something that impressed me most in this millennium was a discovery that one could find this kind of unstable structure, that they could be computed and experimentally discovered. You start in 61,506 dimensions. And this is a little bit like throwing a boomerang. A very skillful person in 3 dimensions can take a boomerang, throw it, and boomerang will come back. Now, in 4 dimension, it's much harder to do that, just because likelihood in coming into the same neighborhood becomes less the harder the dimension is. We never thought it would be possible to do this, but it is. And I'll give you some flavor for how it works in this tutorial. And the deal with this tutorial, you don't need me, you could do it yourself. If you're a professor, you could do this in 10 minutes. This will be a tutorial that doesn't have many equations. It's really conceptual. I just try to focus on the main idea of how is it possible to do this. And the main point of this tutorial is to tell you that when you think of the problems like motions of fluids or atmosphere or what happens at the edge of a black hole, we humans tend to try to visualize them in 3 dimensions. The thing that one has to learn is that you should actually visualize things in state space, which in this case will mean 65,000 dimensions. To make it very specific, we will illustrate everything by so-called plane Couette flow. You have 2 infinite surfaces. The top one here is going away from us, and that's indicated by the red color. So whenever you see a red color, that means streamwise velocity that's going away from us. And whenever you see a blue velocity color, that means the liquid is going toward us. The important directions are streamwise. Most physics will take care in the shearing direction. That's where things really happen. Very important parameters of the systems is the wall normal distance. And the problem can be rescaled in such a way that there is a number called Reynolds number, which will be studied in these examples in so-called transitional regime. This means the regime is when you see structures in this plot. And let me explain in more detail what this plot is. We see a plane that's a midplane between the 2 walls. And in that midplane, the velocity of fluid is 3-dimensional, but in midplane, it's 2-dimensional. It has 2 components. And that's what these little arrows are. So when you see a bunch of arrows goes around, there is some kind of twirl in velocity field in the midplane. We also cut the fluid. It's in principle infinite in streamwise and spanwise dimensions, but in practice, we make it finite. And to be able to solve these problems, we even make it periodic. So we impose boundary conditions that state that the fluid is same on this vertical normal cut to the fluid as over there. And now you see in a 2-dimensional velocity field, and the color, the 3rd dimension, gives you actually the 3rd component. So in this cut, you actually see at one particular section of the flow, the full velocity of the flow. So when the flow starts getting turbulent, then the fluid will be going between the walls and it'll be crossing this midplane. So that's a nice place to look at it. You can simulate it. They are relatively easy to simulate. What you see here is, Reynolds number is 400. it doesn't really matter what this number is, but geometrical meaning is that the structures that you see here are comparable with the spacing between the top wall and lower wall. What I want you to see from this picture is that when you run this kind of simulation, it never stops. And what you see is occasionally it seems to want to get very ordered. You know, you're shearing it, it seems to want to design some rolls. So you say, okay, that's boring. There was a transient and turbulence seemed to be there, but actually died. But it's not so. You approach this transient state and then things go bam, and the whole thing explodes, gets very turbulent. And the task of this presentation is to tell you how to think about it and how to describe such a thing. So this is what we want to describe. And the striking thing about this, it's rich in recognizable patterns. In this case, you know, they call streaks, rolls, vortices, etc. Now, in practice, we are not able to simulate accurately very large cells. But when you do simulations and you don't have a good theory, what people do is they say, well, when I look at this thing, you know, I see that there is a characteristic scale. It's roughly the distance between the walls in this case. So can I make something that captures one of these or two of these rolls, and it's relatively small, so I can compute it. That's called a minimal cell. So what people do, and that's very empirical and not rigorous at all, is they have their nice codes that simulate Navier-Stokes equations, and they make the streamwise direction as short as possible and the spanwise direction as narrow as possible, but not so short and small that everything dies. So they play with parameters, geometrical parameters of the system, until they find a system that seems to capture the main things you've seen in a large simulation, which is there are periods where everything is going bananas, they look turbulent. And then there are periods where the system, you'll see this in a second, tries to organize itself. Like right now, you know, it looks like a stable roll, and then it falls apart. And this repeats itself forever. And we cannot prove it mathematically. We cannot prove that this eventually doesn't become something that's steady and not turbulent. But in numerical and physical experiment, this goes on forever. So how do you hunt? Whenever you have a dynamical system that you don't understand, the first thing you're supposed to do is you're supposed to find its equilibrium, fixed points. So you're supposed to find state solutions that don't change in time. There is a classical solution for laminar flows, which is it's very obvious. You know, when you have two surfaces moving, what Navier-Stokes says that if I put horizontal sheets of different velocities, then there'll be friction between them. Your intuition is that in the middle, there should be no motion. And then you expect the rest to arrange in such a way that you know, the friction is balanced equally between all the layers. And that's called laminar equilibrium. It's totally trivial solution. Velocity is just proportional to the distance away from the center. And it goes to, let's say, +1 in some units to -1 from top to the bottom. That solution has been known forever. But Nagata discovered other solutions. He discovered solutions that are pretty stunning, because when you look at these two solutions and you go back to where we started. In this box, you see both of them. So you see a solution, a glimpse of solution that looks like a wiggle down the middle right now, a wiggle down the middle. And now you look at this solution, and one of them looks like straight rolls, and the other one looks like things are falling apart. And what used to be very hard to explain to professors of fluid dynamics and engineering is that these solutions, they're not turbulent. They have features of which we see in turbulence, but they're pretty amazing because what they are is it's a non-trivial disposition of three-dimensional velocity across the whole volume of this thing. And it has a property that I stick it in my time integrator, it doesn't change in time. So even though it looks like it's supposed to fall apart. So these are equilibrium solutions. And by now we know how to get tons of them, and we have hundreds and thousands for different experimental situations, different geometries. So I'll show you a few more just so you get. So basically, there are other equilibria which have more structures, and there are things that look totally crazy turbulent, and they have, but they are equilibria. They're all unstable in the sense that if you make small perturbation on them, they will fall apart and go back into turbulence. And it's not possible not to make small perturbations on them because your numerical codes have small accuracy, etc. But we can quantify exactly. Now that we have equilibria, we can linearize their neighborhoods. I will not show it unless you ask me. And we can compute the eigenvalues and eigenvectors of linearized unstable equilibrium. The eigenvalues will have a property that there will be few in number, 1, 2, 3, 4. I'll show you some plots in which you're unstable. So if you perturb along eigenvector, which is a picture like you're seeing right now, but now it's just state of flow close to equilibrium. If you perturb in that direction, you fall apart. But the other 62,000 dimensions or million dimensions, they all are negative, so they fall in. Now I have to tell you that in this calculation, our numerical accuracy can be 1 part in 10 to 11. Meaning you have a liter of the fluid, the stuff is moving with velocity of order 1, but the error on velocity field is 10 to minus 11. So these things can be solved ridiculously well. So this was a big deal to be able to find, and that happened in the last century, end of last century, that we could actually find this equilibrium and study their stability for very high dimensional fluid flows, 100,000 dimension. And you haven't asked, but what is the dimension? Whenever you write these fluid flows, in principle, they're infinite dimensional. But if you go to the Fourier-Chebyshev basis, you're forced to truncate this basis. And the dimension in this context of state space just means the number of computational degrees of freedom you're keeping track of as you're solving these equations. They become ordinary differential equations of very high degree rather than dimension, rather than partial differential equations. So this was a big deal to find them, but then something totally remarkable happened. And that was done by Kawahara. He discovered the first periodic orbit. Now let me show you what periodic orbits are. So this just looks like what I showed you before. The thing that looks turbulent gets almost regular, then it's unstable, fall apart, does something. But if you look at upper left corner, it actually has a period which is 75 units. And if I didn't tell you it was periodic, you could absolutely not distinguish it from the other solution, which was turbulent. It never came back. Now, this is a remarkable movie. It's a video that plays and then seamlessly replays itself and replays itself, every 75 seconds or whatever time unit you have. But then it turns out there's another one. Again, we know it's different, but to you it might look like a typical turbulent thing. And you can see it's doing something slightly different. And after 88.9 units of time, it comes back. We have a database. You can just click on it and you can look at, in principle, there are infinitely many of these solutions, but we have tabulated 100 or so for you that you can just run on your laptop if you want to. And it looks like a snapshot of your fluid, but these guys are more amazing because they look like space-time videos of your fluid. So they're tracking the turbulent behavior of the fluid, not only as instantaneous pictures of the state of the fluid, but they're following also for the period of the orbit. So they are a really big deal. And they kind of changed everything. And then once it's like a transistor, once you realize you can make a transistor, you can make an industry out of it. So the main thing about these solutions is we computed them in a minimal cell. But actually, they're exact solutions of the infinite system, but they have one peculiar property that they're tiling the infinite system. You can see this here. We have taken 3 copies, sideways, or 4 copies downstream of the solutions I've just shown you, one of the solutions. The short one, actually, I haven't shown it to you yet. They tile the volume of the cell in a regular way, which is not what you see in experiment. But then the periodic orbit theory is the thing that gives you connection between such tilings and computing expectation values. So what's striking about these solutions is that now I'm showing you sustained turbulence. And, how would you know? It looks like the other guys. It bounces around and then does this typical thing. It gets organized right now. Right now, boom. You think it's dead? No, it continues. So this should be possible to understand and organize because there are very few features and in these flows, and we can see them by naked eyes. So what do we do? Here is something that most people don't get taught, but it was the fundamental idea of Eberhard Hoff in 1948. You should look at the state space, meaning you should peer into 62,000 dimensions. So how do you do that? So I'll explain it. First of all, you need to produce some kind of coordinate system, as orthogonal coordinates are very useful. And it turns out the fluid has orthogonality built in, because when you look at kinetic energy of the fluid, any place in a fluid, you have velocity fields, and you can define in our 3-dimensional frame product of 2 different velocities. And if you identify this velocity divided by 2, you get kinetic energy. So there is a natural way to produce a vector space with 62,000 directions, which has orthogonality built into it. How do you now look at this? So maybe I'll show you this guy first. You can say, well, if I have this equilibrium state, that's a point in a vector space. So it seems like very natural that I use the vector that connects my origin, zero kinetic energy, to that point in 62 dimensions as one coordinate. And here is the idea of global thing. You know, I just told you, when you have a point in a state space visualized in 3 dimensions, it looks like a recognizable solution of the flow. So that's, you know, one of the equilibria, which we call upper branch. And I showed you this picture at the very start. So this corresponds to point in a state space. Now, this system has symmetries, just 2 planes against each other. You can rotate these 2 planes in a 3-dimensional world by 180 degrees. And when you do this, they still have the top one is still going away from you and bottom one is going behind you. So you can do that. Then, you know, you have a regular paving in a spanwise direction, and you can actually move your solution, you know, by the half of the box. And every time you do this, you get things that look very different. This solution is the solution above that has been flipped, and it has a totally different shape. And then when it's translated by half, it has a totally different shape between 4 of these things. So from one equilibrium, you get 3 more for free just by symmetry. But they're very different in shape, which means that when I present them in the state space, they're very distant from each other. Now, I can use these guys and I can add them up and subtract some and add some, and I can show that these combinations are orthogonal under this norm that we constructed, the energy norm, which means now that out of this one solution plus symmetries, I get 4 vectors in a state space. They are 62,000 dimensional vectors, which are orthogonal to each other. And so they are very far apart from each other. They point in totally different directions, but they have been constructed from the solution of the system. So we have right to hope that they will span the important part of the state space. And when we look at these 4 dimensions as opposed to 62,000 dimensions, maybe we'll see something. Let's have a look. And, you know, these are kind of things which you do when you know, decompose things in Fourier modes, but now it's non-linear. It's not some trivial thing. You actually have to solve your Navier-Stokes equations with high precisions. And when you add them up, you get something that doesn't look like a solution, but you know, is a point in the same state space. And for other ones, you get shapes like this. And now what you take is you take your turbulent flow and you project your state onto these 4 coordinates. Are you with me? For example, if I have my fluid flow, here it is, and it's doing its turbulent thing, I can project it onto the base 3, this particular base. And projecting it means it's this orthogonality relation. I multiply this to 64,000 dimensional vectors, and I integrate over all components. Remember what the norm was, and I get a number. It says how much of this fluid state is contained in this direction. I'll remind you what the form was, I take my 64-dimensional vector, which is my turbulent vector, I take a basis vector, I multiply them, I get a number. And that number is projection of a big vector into one of the 4 dimensions I care about. So what happens? It is amazing. So I'll show you. I just take 2 of these vectors and show you what happens. For the turbulent flow you've been looking at all along. Bango, you get Starship Enterprise. The points in this plot are the equilibria we've been studying. So this point here, which we chose to be the origin, is the laminar solution. It's the first equilibrium in these 4 solutions that I showed you. Then there is this thing called upper branch, which was, wiggly but static. It's hiding in there. There's a thing that's called lower branch. If I start along the unstable direction of lower branch equilibrium, in one direction, it just goes and dies. That's this blue line. In other direction, I kick it into the turbulent world, so it actually visits this upper branch and eventually dies. If there is this newbie, which is in the center of the system, which seems to be taking stuff and shrinking everything from 64 dimensions and then spewing it, spiraling out in the plane, and part of it goes toward lower branch and dies, and the other part goes up, etc. So suddenly you have a visualization of what these solutions meant. When we had them individually, it was very, after a while we got bored of them because they all looked like, for some part of time, they look organized, but then they go bananas. But in this dual representation, global state space, you can actually see where they go, who they visit. And that means that you can tile your huge dimensional state space by neighborhoods, and every neighborhood has a name. In this case, the first set of neighborhoods, am I coming close to one of these equilibria? This is in 2 dimensions, but we have 4 at hand in this contraction. So here is what. And now you have to understand this picture is not static. This is actually 1,000 videos put together because every one of these lines that you see is one of the simulations I've shown you, projected onto 4 coordinates. And if you look at it in 3 dimensions, you start seeing very interesting things. In 3 dimensions, there was this multiplicity because I could flip the system this way and sideways, streamwise and spanwise, and it was the same system that was invariance of equations of motions, boundary conditions. And that meant that some equilibria, like the dead one, laminar one, just mapped into itself, but other ones mapped into 4 or 2 copies. So the upper branch has 4 copies. And what's plotted here are various equilibria. There are various dots here. But also what's plotted in is a turbulent flow, the flow that I showed you first that just goes on forever. And what we do here is we strobe it. Every time it runs a little bit, we record it as a dot on this plot and just let it run for a while. And what you see from this plot is that turbulence is chaperoned by these upper branches, unstable manifolds. It doesn't, they seem to push it back in. And, you're not allowed to go down here either. So we are starting to see not only that we can give names to things, but we can start understanding how this turbulence works in a state space. It's localized to something. Let's work this out in more detail. So here is the utility of this new visualization, in which we can think of the same system in terms of infinite dimensional state space on the left and our physical intuition in 3 dimension on the right. So what we do now, we start with a newbie, one of these equilibrium positions, and run our simulation. And nothing is happening. But when we look into the state space, we see actually there's a little motion. Doesn't look like anything here. And the newbie is unstable, so I run away from it. And the fluid is really changing. And it's starting to look like the lower branch. Then I go bananas because I'm coming close to upper branch. And I'm doing all the crazy stuff that turbulent fluid does. And I do all these things we have seen in simulation, but now we know where they're in state space and we can start exploring them in detail. But no, I get kicked out again. So now I'm going really fast, zipping all over the place in 60,000 dimensions. And this goes on for a while. Finally, I find a hole where I can escape the turbulent world, and I calm down, and I calm down, and eventually this thing dies and becomes our equilibrium that we cared about before. So now we have a tool where we can combine our intuition as a plumbers in 3 dimension with our amazing tools of nonlinear dynamics in state space by finding first close recurrences. And here is the dual visualization of a periodic solution. So it's happening. This is turbulent. This is periodic orbit. Periodic orbit is orange in state space. When I'm black, I'm close to it, and you can't tell by eye the difference between them. So I'm shadowed by a periodic orbit. Until ... I run away, and periodic orbit does its thing, but I'm just doing my turbulent thing. So that illustrates the crucial part of why we use periodic orbits to describe chaotic or turbulent systems. They're shadowed by periodic orbit, and if you have a good theory, which is periodic orbit theory, you can turn this into computation. So you can compute all the averages, compute ergodic orbit by averages computed by turbulent orbit. So this is totally beautiful and stunning. And the next simulation, I showed you originally that it looked like the upper branch had this unstable equilibrium planes or semi-spheres, and the turbulent flow seemed to be captured, chaperoned by them. Now we can see how this works by simulations where you have a periodic flow and how it visits various neighborhoods. And you realize that actually now it's behaving like this neighborhood, and now it's behaving like some of the crazy stuff below. So while the unstable equilibria of Navier-Stokes captures some features of the flow, the unstable periodic orbits of Navier-Stokes actually are embedded in turbulent sea, and they capture a great deal of what you see. So here's another example. This is a solution that does a little twiddle dance, doesn't have a symmetry, goes over there. So it's different from the one I showed you before. And it's exploring different part of the state space. So we have amazing, powerful tools to, map out turbulence and illustrate it. It's a month's amount of work. Doing this for fluids is much harder than doing it for one-dimensional Kuramoto shear. Here's an example. But it only counts in engineering community if you can do it for the real case. And we can do it, and you can do it. So to summarize, it used to be that turbulence was a bunch of things. Originally, people had wind tunnels and they would put one hot wire in the wind tunnel. Today, it's totally amazing. When you have an experiment, you can extract from it very detailed three-dimensional velocity data as a function of time. And we have a theory that says this is all suspended on a very rigid skeleton of equilibria and spacetime periodic solutions. And now that you have this, you can design things or control things because you understand the stable, unstable manifolds of these solutions, which tell you how you have to affect the flow in space-time, what kind of perturbation you have to give it to control it or make it go someplace where you want to go. In state space, what needs to be done is ahead of us, as is always our life in research. And you're very interested in this. You can read some of the literature, and you can click on this link for channel flow. Download the simulation software and do all these calculations I showed you.